welcome to part 2. Let's finish this up, shall we? So we are looking at point O is the center of each regular figure. So we're taking a look at this figure right here. And we want to know what is the image of point D under a 180-degree rotation about O. Okay, so we can consider this as being the origin. So if I kind of have an imaginary axis, X and Y axis here, 180 degrees is going to be 2 rotations. So if D is right here, one rotation is going to represent 90 degrees because we have ourselves a square here. If it's a square, has a degree rotation of 90 and an order of 4. So that means if I'm going to rotate 90 degrees, that's going to put me at F, and then if I rotate another 90 degrees, that'll put me at I. So I'm looking at point I for A. Part B, what is the angle of rotation of B onto H? Now, if I take and I erase this, and now I'm taking a look at the hexagon portion, the hexagon is regular. So we have 6 sides with the hexagon, and that means it has an order of 6. Order of 6 because it's a regular polygon, and in a regular polygon, the order of rotation is equal to the number of lines of symmetry. Okay, so that means that each order, if I know that the whole symmetry, one distance around is 360 degrees, divided by 6, that means each rotation is going to be 60 degrees. So each rotation, 60 degrees. So if I'm looking at B going to H, I'm going to choose whether I want to go clockwise or counterclockwise. Well, it's going to be easier to go counterclockwise to get there. So one rotation from B to get me to the next one is going to be 60 degrees. Then if I go from J over to H, that will be 60 more degrees. So that's 2 rotations of 60 degrees, which is going to mean 120 degree rotation counterclockwise. Counterclockwise. There is a difference, as we know, between clockwise and counterclockwise, and we want to make sure that that is known. If we take a look at C, C is saying what is the image of J under a rotation of 120 degrees counterclockwise. So this is almost identical to what we just did in part B, but now we're starting at J. So again, this means each rotation, as we said, is 60 degrees. So that means 120 degrees will be 2 60-degree rotations. Not rotations, rotations. So one rotation, 60 degrees, is going to be to H, and then another 60-degree rotation will end us at G. So point G is the answer that we're looking for on part C. Number 30, we want to rotate the word HI, which is shown below, in a 270 degrees counterclockwise about the origin. So we have our origin here. And 270 degrees. We haven't talked really about 270 degrees too much, but 270 degrees is 3/4. It's 3/4 turns. So it's 3 times 90 if we want to think of it that way. Well, a 270-degree turn counterclockwise, if I want to look at it this way, would end up right here. So because this is 90 degrees here, 90 degrees here, 90 degrees here, that would be 270 degrees. So, but instead of me rotating it 3 90-degree rotations, I could go the opposite direction. If I went counterclockwise, and I went from here counterclockwise, that will get me to the same location. So if I do 90 degrees clockwise, that will be the same as a counterclockwise of 270. Either way is fine, but I would rather rotate it once than 3 times. So how do we come up with the 90 degrees? So I always take 260 minus 70 to give us a 90-degree rotation clockwise. Okay, And as we mentioned before, if we're going to take and rotate 90 degrees, that means, remember, a rotation of 90 degrees is a switch in the X and Y axis, their coordinates, and we want to follow the signs of the quadrant it ends up in. Okay. So in this example, we start in quadrant 1, which is positive, positive. Okay. But then when we rotate it 90 degrees clockwise, we are going to end up in quadrant 4, which will mean that we will now have signs that are positive, negative, which in this case we're not even really dealing with coordinates, so it's not that big of a deal. But if it's going to be helpful for us, we can look at it this way. So now I'm going to rotate this. So here, okay, this is at 1, 1. So what's going to happen is that if I rotate it 90 degrees, it's going to end up down here, right, where the X and Y are switched, and now it's positive, negative. So everything that's going to be here is going to be rotated this way. And once I have that, then I can just follow. This is going to be the side for the H. I know that the middle is going to be down 2 for the H. Okay, and then the I, if you haven't noticed, it says high. Then those are going to be connected, and I can just follow the pattern from there. So if we take a look at this next question, we're almost done. Composition of reflections into what? What type of line? So what they're looking for here is going to be parallel or perpendicular. That's the type of lines that we are referring to, which is going to be a translation. Okay, so if I make up an example. So suppose that I have the letter P, and I'm going to be reflecting this in 2. So there's 2 lines. So either parallel, okay, either these 2 lines are parallel, or I'm looking at perpendicular lines. Okay. So that's sort of the same thing, what I would look at. So if I am starting with the P, with the original, if I reflected it across this line, it's going to look like the opposite. So the P is going to be flipped to be a mirror image. If I then took and reflected it across another line, the line parallel to that, the reflection of that will make it look like the original. And so that means is going from this first one to the second one, that would be happen in 2 parallel lines. So a double reflection across parallel lines, 2 parallel lines, will result in a translation. That's just the theory question. If, and I believe the next question asks in a couple minutes, so we'll wait till then. Okay, number 32. In the diagram below, we got lines T and R are perpendicular. You can't really see it on here, it's cut off, but this is going to be line T. And we want to name the image of FEH after a reflection in the line, and then R, and then a reflection in the line T. So let's start with FEH. So we want to start with this. The first thing that we're doing is that we're reflecting it across line R. So that's going to be our vertical line. If I reflect it across that line, that's going to be a mirror image. So C is the same distance away as F is from line R. And then if I follow the pattern, reflection across line R will end up with triangle CDA for me. So that's the first reflection. The second reflection, then I'm going to take CDA and I'm going to reflect it across line T. So now line T, what was top is now going to be bottom. So I'm seeing, okay, A and N, those 2 are reflected across the x-axis, or line T in this case. So therefore, N is going to correspond to A, D to O, and P to C. So after I reflected it across line T, my end result is going to be triangle, in order the letters always matter, P-O-N. Part B, excuse me. Part B, what single transformation is the same as two reflections in two perpendicular lines? So this is going back to what we're just talking about right up here. And so we just did this example right here. If you notice, if you look at this, part 1 with FEH started out in quadrant 1. And then our final reflection ended up in quadrant 3. So the corresponding point ends up being negative, negative originally, excuse me, after it's transformed in positive, positive. So that means really, if we know our patterns between these two guys, that means that it's going to be a rotation of 180 degrees. Because when you have the original rotation of 180 degrees, just changes the x and the y values. Moving on to the number 33, we want to determine, my apologies, my computer is not working so well. We want to determine the number of lines of symmetry, if any, for each figure. And it says polygons that appear regular are regular. So once again, it never hurts to define again what a regular polygon is. It means that all angles and all sides are congruent. Okay. And in class, when we were talking about lines of symmetry, so remember that means that we can draw in a line and the two halves are identical. Okay, and we said if, in class, if it's a regular polygon, then the number of sides, n, will equal the number of lines of symmetry. So in this first case, we're looking at a pentagon, and a pentagon is going to have 5 sides. If I go through each of the 5 vertices, I'm going to have 5 lines of symmetry. So I know that for a fact because, excuse me, it is going to be 5 lines. Part B, we have ourselves a parallelogram here, but I would say it's a little bit more than a parallelogram. So I would say this is a rhombus. And if I have a rhombus, I can go through 2 diagonals and have 2 equal parts. Now, if it is a parallelogram all on its own, just a parallelogram, it will not have any lines of symmetry, which drives a lot of students nuts because it doesn't make sense. But a parallelogram just on its own will not have lines of symmetry. Okay, but since this one is a rhombus, it will have 2 lines through the 2 diagonals. Part C, we're looking at ourselves at a circle. Now, if you think a line of symmetry is going to be thought of as a diameter, and if we've talked about diameters, we know that we can have an infinite amount of diameters and radii in a circle. So in this case, we're going to have infinite, when it comes to a circle, infinite amount lines of symmetry. Number 34. We're taking a look to see which of these have point symmetry. So a quick review, point symmetry means if we rotate it, careful, make sure it's a rotation, it's not a reflection of 180 degrees, and looks the same as the original, then it's said to have point symmetry. So is it the same upside down? That's what the question is. So let's go through the alphabet here. Okay, I'm going to say A. If I turn that upside down, it's going to look like this, and that's not going to work. So no, I'm not going to say A doesn't work, B doesn't either. Actually, there's only a few. C, D, no, E, F, G. When I get to H, if I turn H and I rotate that upside down, it's going to look the same right side up. Same thing for I. J and K, no, L, no, N. If I turn N upside down, it is going to look the same as it does right side up. O, that one's pretty easy. P, no. Q, no. R, no. S, yes. If I turn that upside down, it's still going to be the shape of an S. And the only other one, or other two that we have, will be X and then Z. So those have point symmetry. Once again, meaning if I turn them upside down, they look exactly the same as the original. We take a look at the last two questions. 35, draw in all lines of symmetry if given, or if any, for each figure below. So here we just have ourselves a quadrilateral. It's just going to have one horizontal line. This next one over here, it's an isosceles triangle, and as we know, all isosceles triangles have that line of symmetry, which is the median, the perpendicular bisector, angle bisector, all that fun stuff. Finally, number 36, find the angle of rotational symmetry of an octagon. Okay, so remember, rotational symmetry, as we said, means that, again, this is a regular octagon. It doesn't say that, but it should say that's a regular octagon. So it has 8 sides. Remember, full rotation, or a full revolution, if I should say, is 360 degrees. So if I want to find one of those rotation, I'm going to take 360, the whole, divided by the number of sides. And so, because it will have a degree, have an order of 8. Because again, it's regular. So the number of sides is equal to the lines of symmetry and the order of rotation. So finally, if I take 360 and I divide it by 8, I'm going to have 45 degrees. And that will represent the angle of rotational symmetry of an octagon. Okay? Go back and review, pause, and replay where is necessary. Be ready to come in and ask questions, and good luck on the test.